So this is Unit 9 for the GCSE Physics only. Electromagnetism. This is the last unit, the last one of these videos. Okay, so our objectives then. We've got 6 objectives from this unit. You need to be able to describe the key magnetic fields. You need to understand how a wire and a magnetic field interact. Use that to describe the function of a DC motor. Describe how a current can be induced in a wire. Describe the function of a simple AC generator. And then describe and explain how transformers work, which basically brings in everything that we've done in this unit. Okay, so we've got our useful links. Some of these have got stuff that's not 100% relevant to GCSE, but it's extra depth and good stuff still for you to know, especially if you're thinking of studying physics beyond GCSE. Don't forget Seneca. Again, go back to video 1. The link to Seneca is in video 1. Okay, so the magnetic field shapes you need to know. So, magnetic fields. We call these B fields. They're called B fields because somebody liked the letter B, and that's pretty much it. There seems to be no other reason. So there we are. And that's the symbol for magnetic field strength, which is also known as magnetic flux density. Now we measure this in Tesla, which has the symbol of capital T. However, 1 Tesla is huge. So you tend not to see anything in Tesla in the work that we do. It tends to be in nano times 10 to the minus 9 Tesla, or milli times 10 to the minus 3, micro as well times 10 to the minus 6. Also remember, magnetic field lines always go from north to south. Now, there are 3 magnetic fields you must learn. And here they are: the bar magnet, the solenoid, and the current carrying wire. So you've got your different shaped magnetic fields, but there's some rules to help you to remember the different shapes and how to draw them. So for the current carrying wire, we call the right hand corkscrew rule. So you place your right hand, your thumb, in the direction of the current, and your fingers curl round to make an OK sign or a thumbs up sign, and your fingers are the B field that curls round, and that's the current. For a solenoid, same hand, but we do it the other way around again. So this time you curl the fingers in the direction the current is going in the coils, and your thumb points towards north. Okay, so the motor effect then. Now if you have 2 magnetic fields, they interact. Hopefully you're well aware, north and north repel, south and south repel, and opposites attract. So a current carrying wire has a magnetic field. So if you bring it inside another magnetic field, you're going to create a force. We call this the motor effect. It's also called the Lorentz force as well. Now we calculate this with this formula: F equals BIL. F is force in newtons, B is magnetic field strength in Tesla, I is current in amps, and L is the length of the wire inside the magnetic field in meters. Now we use Fleming's left-hand rule. Calculate the direction of the force. So this is Fleming's left-hand rule. So you take your left hand and you put it like this. You put your thumb is motion, your first finger is field, and your second finger is current. And what you do is you have to rotate your hand round. You'll be given 2 and trying to work out the third, and you have to rotate your hand round to try and get it right. Okay, so our motor then. So if we place a coil of wire inside a magnetic field, this means that in one direction our current will be going one way, and in our other direction our current will be going the other way, and this means that one side is pushed up and the other side is pushed down. This causes our coil to rotate, and this is a motor. Okay, then we have a commutator which switches the current every half turn. So the piece of wire that was going up, as it's going down, the commutator swaps the current so that that one going down now has the current going through the other way and continues the motion. We also have carbon brushes. These stay attached to the wires on the external circuit, and allow the commutator to stay connected. So rather than physical wire connections that get twisted up, these carbon brushes just brush up against the commutator, and as carbon's low friction and a conductor, it's brilliant for doing this job. Okay, so here's our diagram that shows all these things I'm talking about. Okay, induction then. The motor effect can be reversed. So if we put motion in, we create or induce a current, and this is why it's called induction. All you need is relative motion. Okay, so what that means is either the wire or the magnetic field can be moving, doesn't matter which one. A moving magnetic field, we can also create in a solenoid if we use AC. So alternate current where it flips backwards and forwards. Doing this, we can actually create a moving magnetic field inside a solenoid. Now Fleming's right-hand rule gives us the direction of the induced current, so exactly the same as the left, but this time using our right-hand rules. We have our field, our motion and our current. It's the other hand because it's reversed. Okay, so the AC generator. So the easiest way to have constant motion for the wire is to make it a coil. Yeah. If we rotate that coil inside the magnetic field, we induce a current in the coil. This creates an AC current as the amount of coil inside the field is constantly changing, but is also the wires are changing direction. Now we have slip rings. So slip rings, if you look in the diagram, are connected always to one side of the wire or the other. So as this side goes up, the current will be induced one way. As this side goes down, the current will be induced in the other way, and so on and so on. Okay, so we can make motors and generators better by doing the following things. If we make a motor, to make a motor spin faster, we increase the current, we increase the number of coils, we increase the area inside the coil, or we increase the strength of the magnetic field. It's important you put strength in there. To make a generator turn faster, to make a generator generate a large current, you basically can do similar things. You can increase the number of coils. We can add a soft iron core because soft iron focuses the magnetic field. You increase the area of the coil. You increase the speed you rotate it. The only problem with increasing the speed is you also change the frequency of the AC. Again, changing the strength of the magnetic field will change the current that you generate. Now, transformers are an application of electromagnetic induction and the motor effect. So, transformers, they take only AC, they only work with AC because you need that constantly changing magnetic field. So you have AC current in our primary coil, creates a change in magnetic field in their iron core. Remember iron, because iron core focuses the magnetic field. Then this change in magnetic field is passed through the core to the secondary coil. Change in magnetic field inside a coil of wire induces a current in this secondary coil. Now if you have a look at a transformer, what you'll see is that the iron core is laminated, so it's all little bits of iron stuck together. This increases their their efficiency, increases decreases the amount of energy that's lost due to other magnetic fields going in there. Now how this occurs, that's for A level, not for now. Now the ratio of the coils gives us the ratio of the voltages. So we have this formula, V1 over V2, so the voltage in the primary divided by the voltage in the secondary equals the number of coils in the primary divided by the number of coils in the secondary. And here's our diagram of our transformer with our primary coil on this side and our secondary coil on this side, and you can see the focused magnetic field being passed from one to the other. Okay, so over to you. Have a go at these questions. Either click the link in the description below, or if you close this PowerPoint and reopen it and click on this document, it will open as the PDFs. Okay, so we're now going to look at electromagnetism questions. Some of these are going to tie in other stuff, just because it's the final module of unit or the final unit of the module. So you'll have done everything else, so we might see some other questions. Okay, so wind turbines, a whole load of stuff about wind turbines. Then we've got a graph showing that you don't get constant power. Key things from this graph is to notice that the cut-in speed 3.5 meters per second, and we've got a cut-off speed of 25 meters per second. So if the wind goes out of that range between 3.5 and 25, we don't get any power. So let's then have a look at the rest of the information. The mean wind speed for different times of the day is shown on graph 2. Okay, that's fine. We never go above the 25, but interestingly, we never go above the 14 either. If you look, the max is 5.5, so we're always in this range down here, which is going to be interesting as well. It is claimed that wind power is always a useful backup at times of high demand, which are between 6 and 10, and between 4 and 8, because it's always windy. Right, so explain whether the information in both graphs supports this claim. Well, first things first, we need to talk about the graph. So, well, if we say, let's put down what we've learned. So from graph 1, oops, we're a bit low. Let's just move the paper easier. From graph 1, we know that we need a wind speed that is from 3.5 to 25. If it's outside of that range, wind speed between to get power. We also know that we need a wind speed of greater than 14 for max power. Okay, so if you look at that graph, on average, if we now look at graph 2, well, between 6 and 10 we're going to just about get power. So between 6 and 10 we would generate some power, as our wind speed is greater than 3.5. However, if you look at between 4 and 8, 4 to 8, between 4 and 8, well, between 4 and about 7, we're going to get no power. So, in this range, between 4 or 1600 through to 1900, our wind speed, wind speed is below minimum. So, no power is generated. So all in all, no, that claim is wrong. Claim is wrong. Always write that down. Make it a general statement about the claim. The claim is wrong. Yeah, so because between, in this region here, from here to about here, you know, we're below the 3.5 threshold, we're not going to be generating any power. Okay, so we've got a wind farm. Has an output voltage of 16 kilovolts, a total rated output power of 24 megawatts, connected to the national grid by a transformer. The transformer has an input coil of 400 turns and an output coil containing 4,800 turns. Assume that it's 100% efficient. Calculate the output voltage in kilovolts. Well, because the input voltage is, the input voltage to the transformers in kilovolts, we can just work in kilovolts all the way here. So we have Vp over Vs equals Np over Ns. That's on our data sheet. We want here Vs. So Vs equals Np Vp all over Ns. So that's going to be NP, which is going to be number of turns 400 times our 16. I've done my sum wrong. This sum is the wrong way round. I'm going to multiply by NS. This sum is the wrong way round. Let's start this question again. Okay, so a wind farm off the coast of Wales has an output voltage of 16 kilovolts, total rated power 24 megawatts, connected to the national grid by a transformer. Our transformer has an input coil of 400 turns and an output coil of 4,800 turns. Calculate the output voltage of the transformer. So, we have the equation Vp over Vs equals MP over Ns. We've got that equation where P is primary, S is secondary. So if we want Vs, Vs equals, so Vs is going to go up there. We need to put Ns up there and MP down there, which is probably now a bit confusing, but we're going to get Vp Ns over MP. Or we're going to get 16. Now, because all of our values are already in kilovolts, we can just work in kilovolts. So we're going to get 16 times Ns 4,800 all over MP 400, and that gives us a value of 16 times 4,800 divided by 400, a value of 192 kilovolts, which is, yeah, fine. If you watch stuff on national grids, said the super grid, the highest voltage is 400 kilovolts, so yeah, that would work, that's about right. Okay, calculate the output current of the transformer. So P equals IV. Now we do want to work in, we want to answer in amps, so we need to work in our base units. I is P over V, so our power is 24 mega times 10 to the 6, divided by our output voltage, 192 times 10 to the 3. That's going to give us a current of 24 times 10 to the 6, divided by 192 times 10 to the 3. Gives us a current of 125 amps. Explain the role of transformers in the national grid. Okay, so we step up to reduce current, to reduce heating, to increase efficiency. We step down to make voltage safer for consumers. 3 marks, 2 are going to be for this first statement and the second one for why we have stepped down. Okay, explain the purpose of the iron core in a transformer and state why is it laminated. So, the purpose is to increase and focus or transfer the magnetic field. And why is it laminated? Laminations reduce energy losses. 3 marks. We increase and focus the V field, 2 marks, and 1 for saying about energy losses. Okay, so we've got 3 magnetic fields. The box or below diagram which correctly shows magnetic field pattern around a current carrying wire. So the way to remember about magnetic field pattern is with the right hand corkscrew rule. So put your thumb in the direction, fingers curl round in circles. So it's got to be the one that's a circle, which is that one. Diagram below shows a simple electric motor. When there is current in the coil, it experiences a force due to the magnetic field and starts to spin. State one way in which the coil could be made to spin in the opposite direction. Well, we could put the current the other way, or we could reverse the magnetic field. Let's go for reverse. Reverse magnetic field. Two ways it could be made to spin faster. We could have a stronger B field, or we could have a larger current. We could have more coils as well. Would also make it spin faster. Okay, so rechargeable toothbrushes. If you've ever noticed on a rechargeable toothbrush, you put them on the stand and they charge, but there's no physical contact. If you look, there's no metal there. So it is a form. This is basically how all wireless charging works. It uses, two transformers. So how is the voltage produced in the secondary coil of the transformer? Okay, so whenever transformers work, the steps we have to remember is we have an AC current in the primary, induces alternating B field in coil. Alright? Then we get the B field, or the B field, then induces a current in the secondary coil. 100% efficient just means that no energy is wasted, so power in equals power out. Okay, secondary coil inside the toothbrush has 480 turns. The primary coil has 9,200 turns and is connected to mains. Use an equation from page 2 to calculate the voltage across. So this is what we've just saw before. We can write it the other way up, so it makes rearranging easier. Vs over Vp equals Ns over Np. And Vs is going to equal Ns Vp over Np, which equals 480 times 230 all over Np, which is 9,200. Volts makes a lot of sense. Low voltage. Given that the current produced in the secondary coil is 100 milliamps, use an equation to calculate the power of the toothbrush. So P equals IV. We're going to use 100 times 10 to the minus 3 times by our 12. .2 watts. Simple as for that one. Nice and simple. Okay, so we now got a transformer used in laboratory equipment. State, draw one line for each label. So A is our AC input supply. B is our primary coil. C is our secondary coil, and D is our laminated iron core. The diagram shows a step-up transformer. Complete the sentences by underlining the correct word. A step-up transformer that is 100% efficient will make the output voltage bigger. Yeah, if it's step up, make it bigger. Make the output current smaller, and will make the output power stay the same. 100% efficient. What goes in must come out. Okay, so we now got another transformer. Supplies a village and a business. Excellent. Oh, look at that. We've got a what we call a centre tap. It's not quite a centre, but a variable transformer. Use an equation from page 2 and information in the diagram. Calculate the voltage supplied to the business. Okay, so start off, what we're going to do, our equation is the same one. We want Vs, the secondary voltage, divided by Vp equals Ns over Np. So the supply voltage is going to be the number of turns times by the primary voltage all over the number of turns on the primary. So that is going to be 500 times 132,000 all over NP 154000, which equals 500 times 132,000 over 154000, 429. Let's make it 430 volts. During a severe storm, the connections from the transformer were altered by a falling tree. The village is now connected between A and C. Explain what effect, if any, this would have on the voltage supplied to the village. So we're turned between A and C. So instead of being 268 turns, we're now going to be over the full 768 turns. So the problem we've got here is we're going to increase the voltage. Okay, so increased voltage as village is now connected to all 768 output turns. State what effect you'd expect to have this to have on the village. Well, if you're going to increase massive amounts, you would see power cut. Maybe even a fire. If you're going to supply it with massive amounts of voltage, you're going to see sparks, you're going to get fire. Explain what effect this would have on the, if any, on the business. You may well see that the business you would probably see that the business would probably receive so page has moved. Back where it should be. The business now would receive no power as the village has short-circuited the supply. That's a horrible question, that part 3. That's what I wrote for anyway. If you think any different, put a comment in the comments below, or if you're watching this in school, send me an email. Okay, so we're now going to describe how a transformer works. So transformers work by, as we said before, we have AC current in primary, induces B field in coil, core transfers field to secondary, where it induces a current. Anyway, that's how transformers work. Okay, so we've now got a wire being moved in a magnetic field between two permanent magnets. By using one of the letters of the diagram, state which direction the wire needs to be moved so the current is induced in the direction shown. So, induction uses your right hand, because induction and right both have eyes in them. The other way to remember is motors drive on the left. Anyway, so we now need to put our hand in the thing. So remember, thumb is our motion. This is the one we're looking for. First is field, goes from north to south. Second is current, so we want the current going down like this. The field goes like this, as I'm looking at it on the screen, so the motion goes up. So we're going to write a U for up. It would help if I actually wrote it on the line. There we go. The racing car game uses a transformer. It changes 230 volts to 12 volts by using two coils, A and B. Which coil would have the bigger number of turns? Well, that's got to be coil A, as voltage is proportional to the number of turns, and we need to step down voltage. Yep, so A's going to be bigger because voltage is proportional to the number of turns. So we want the larger voltage on the input side. Right then, state why the input voltage has to be alternating for a transformer to work. We need an alternating, or a changing, let's put changing, B field. And that's the only way we're going to get it with a fixed current. One function of the iron core is to increase the strength. State the other is to focus or to transfer the B field from the primary to the secondary, and that's how you write primary and secondary in shorthand. State why an output voltage is produced by a transformer. Changing field induces a current. Coil has 18,400 turns. Use an equation to calculate the number of turns on coil B. Okay, so if you read, let's just go very quickly back. We want to go down to 12, so we've got, or do we ultimately want NS? So we want NS over NP equals VS over VP. So NS equals VS NP over VP. So that's going to be 12 times 184000 over 230, which is going to be 12 times 18400 all over 230, exactly 960 turns, which is good. So hopefully that's helped with transformers and all that stuff, and hopefully going through these videos you will have improved your exam technique, ready for your upcoming exam. Thank you for watching. Okay, thanks for watching this video. Well done for making it through right the way to the end as well. If you liked it, click like. If you got any comments about stuff that's missing, any improvements, anything you didn't understand, leave them in the comments below. If you look around me, there should now be the playlist for all of these videos, along with YouTube's algorithm recommended one of our other videos that you should go and watch. Also, don't forget to subscribe to the channel, follow us on Twitter, link in the description, just to see the other sort of stuff that we produce.